Have you ever really stopped to think about the invisible forces holding molecules together? What makes a diamond so incredibly hard or Kevlar strong enough to stop a bullet? It all comes down to how atoms share electrons, and it's actually way more complex than just drawing dots and lines. Today, we're doing a deep dive, really getting into the heart of covalent bonding, going beyond those simple models into the fascinating world of electron orbitals. We're unpacking a key chapter from Zumdahl and DeCoste's chemistry, the 11th edition, specifically the one on covalent bonding orbitals.
Yeah, our goal today is really to demystify some pretty core concepts, things like hybridization and molecular orbital theory. We want to show you how understanding these models gives you a kind of shortcut, really, to appreciating why molecules have the shapes they do.
And why materials have certain properties, right?
Exactly. Why Kevlar is strong, why water is bent, even, what gives chili peppers their kick. It's like getting a behind-the-scenes look at the chemical architecture that, well, makes up everything.
And this isn't just abstract theory for an exam. Understanding these models helps you grasp the fundamental logic behind chemical behavior. It provides a framework, so you don't get bogged down in just memorizing facts. Okay, let's dive in. So you probably remember the localized electron model from maybe an earlier chapter, using Lewis structures and VSEPR theory to predict electron arrangements and shapes. It's super useful.
Incredibly useful, yeah. It gives us a great starting point. But it hits a bit of a snag sometimes when you try to square it with the actual atomic orbitals involved in bonding.
How so? What's the mismatch?
Okay, think about methane, CH4. Classic example. Carbon has, in its valence shell, 1 2s orbital and 3 2p orbitals. Now, if carbon used these orbitals just as they are, you'd expect, well, the 3p orbitals are at 90 degrees to each other, right?
Right.
So you'd predict 3 CH bonds at 90 degrees using those p orbitals, and then maybe one different bond using the s orbital. But experimentally, that's not what we see at all.
No, methane is perfectly tetrahedral. All 4 CH bonds are identical with angles of 109.5 degrees.
Exactly. So the native atomic orbitals just don't fit the observed geometry. The model needed an upgrade.
And this is where hybridization comes in. This is where it gets really interesting, I think.
It really is. The idea is that the carbon atom doesn't use its 2s and 2p orbitals separately. Instead, it kind of mixes them, blends them together, to create 4 brand new identical orbitals. We call these sp³ hybrid orbitals.
Okay, so sp³ because it mixes 1s and 3p orbitals.
Precisely. And the beautiful thing is, these 4 sp³ orbitals naturally arrange themselves in a tetrahedron, pointing towards the corners, giving you exactly that 109.5 degree angle.
It's like baking a cake. You don't use flour, eggs, and sugar separately in the final product. You mix them into a uniform batter, that's your hybrid orbitals, which then gives you a consistent cake structure, the methane molecule.
That's a great analogy. And this isn't just for methane. Look at ammonia, NH3. Nitrogen also undergoes sp³ hybridization. 3 of those sp³ orbitals form bonds with hydrogen, and the 4th one holds the lone pair of electrons.
But the underlying electron geometry around the nitrogen is still tetrahedral because of those 4 sp³ orbitals.
Exactly. It provides a consistent framework.
Okay, so sp³ handles single bonds and tetrahedral shapes. What about molecules with double bonds, like ethylene, C2H4? That's trigonal planar, 120-degree angles.
Right. Different geometry needs a different mix. For ethylene, each carbon is surrounded by 3 effective electron pairs, demanding that trigonal planar shape. So instead of mixing all 4 orbitals, carbon mixes its 1 2s and 2 of its 2p orbitals,
giving us 3 sp² hybrid orbitals.
You got it. And these 3 sp² orbitals lie flat in a plane, pointing 120 degrees apart, perfect for trigonal planar. But here's the crucial part. 1 p orbital is left over. It remains unhybridized.
And where does that one go?
It sits perpendicular to the plane of the sp² orbitals. Now, the sp² orbitals overlap head-on between the carbons, and between carbon and hydrogen. This head-on overlap forms what we call sigma bonds, denoted by the Greek letter xi. Think of it like a direct handshake.
Okay, strong, direct connection along the line between the atoms. That's the sigma bond framework.
Exactly. But now you have those unhybridized p orbitals, 1 on each carbon, stinking up and down, parallel to each other. They overlap sideways, above and below the sigma bond axis.
Ah, like a high five happening across the handshake.
Kind of, yeah. And this sideways overlap forms a pi bond, denoted Hase. So a double bond isn't just 2 identical bonds. It's always made of 1 strong sigma bond and 1 generally weaker pi bond.
That's a really key takeaway. 1 sigma, 1 pi for a double bond. And those pi electrons, being more exposed above and below, are often where reactions happen, right?
Absolutely. They're more accessible, making double bonds centers of reactivity in organic chemistry.
Okay, so sp3 for tetrahedral, sp2 for trigonal planar. What about linear shapes, like carbon dioxide, CO2? Carbon's making two double bonds there, 180 degrees.
You're following the pattern perfectly. For a linear arrangement, carbon needs only two directions. So it hybridizes its 1,2s orbital with just one 2p orbital.
Creating two sp hybrid orbitals.
Exactly. Oriented 180 degrees apart, giving that linear geometry. And this time, it leaves two p orbitals unhybridized.
Okay, so two leftover p orbitals perpendicular to the sp axis and also perpendicular to each other.
Right. The sp orbitals form the sigma bonds, like in CO2, one sigma bond to each oxygen. Then, those two unhybridized p orbitals on the carbon can form two separate pi bonds, one with each oxygen. Or, in a molecule like acetylene, C2H2, the two carbons form a sigma bond with their sp orbitals, and then the two unhybridized p orbitals on each carbon overlap to form two pi bonds between the carbons.
So a triple bond is one sigma bond and two pi bonds.
Precisely. And you see this in the nitrogen molecule, N2, as well. Each nitrogen is sp hybridized. One sp orbital holds a lone pair, the other forms the sigma bond. The two unhybridized p orbitals on each nitrogen form the two pi bonds, creating that incredibly strong N2 triple bond.
That explains why N2 is so stable and relatively unreactive. Okay, what about elements that break the octet rule, like phosphorus in PCl5 or sulfur in SF6? They need 5 or 6 directions.
Yeah, the model extends to accommodate those too. For 5 electron pairs needing a trigonal bicaramidal shape, like in PCl5, we invoke dsp³ hybridization. That's mixing one d orbital, one s, and 3 p orbitals.
And for 6 pairs, octahedral, like SF6.
That would be d²sp³ hybridization, 2 ds, 1 s, 3 ps. Now, it's worth mentioning, more advanced calculations suggest d orbitals might not be as involved for these main group elements as this simple model implies.
But for understanding the shapes and having a consistent model at this level, dsp³ and d²sp³ are still really useful concepts.
Exactly. They provide the right number of hybrid orbitals with the correct geometry. So the overall strategy with this localized model is, first, draw the Lewis structure. Then use VSEPR to figure out the electron-pair geometry. Then you pick the hybridization scheme that matches that geometry.
It's all about tailoring the atom's orbitals to fit the molecule structure for the lowest energy. It's pretty powerful. You know, it makes me think of Stephanie Kolek, the inventor of Kevlar. Her work relied on understanding how these long polyimide chains could align perfectly, forming incredibly strong fibers due to, well, precisely engineered molecular structure and the strong covalent bonds involved. It's a testament to controlling this stuff.
Absolutely. That precise alignment and strong bonding, likely involving concepts related to this chapter, is what gives Kevlar its amazing properties. But, for all its strengths, this localized electron model, even with hybridization, isn't perfect.
Right. You mentioned resonance earlier. That's always felt like a bit of a patch, forcing electrons to be in multiple places at once because the simple model can't handle it.
Exactly. It struggles with delocalized electrons, electrons shared over more than two atoms, and it also doesn't easily explain molecules with unpaired electrons or give us direct information about bond energies.
So that led chemists to think, maybe electrons aren't always localized between just two atoms. Maybe there's a different way entirely.
Precisely. This is where the molecular orbital MO model comes in. It takes a fundamentally different approach. Instead of starting with atoms and modifying their orbitals, it says, when atoms combine, their atomic orbitals essentially disappear and are replaced by completely new orbitals that belong to the entire molecule.
Okay, so not atomic orbitals anymore, but molecular orbitals. How does that work? Let's take the simplest molecule, H2.
Perfect example. You start with 2 hydrogen atoms, each with the 1's atomic orbital. According to MO theory, these 2 1's orbitals combine to form 2 molecular orbitals.
2 atomic orbitals in, 2 molecular orbitals out. Makes sense.
Right. One of these MOs is called a bonding molecular orbital, labeled SWUNS. It's lower in energy than the original 1's orbitals. Why? Because the electron density in this orbital is concentrated between the 2 hydrogen nuclei. This attraction holds the atoms together. It favors bonding.
Okay, lower energy, more stable, holds things together. What's the other MO?
That's the antibonding molecular orbital, labeled 1's with an asterisk. This one is higher in energy than the original 1's orbitals. Here, there's actually a node, a region of 0 electron probability right between the nuclei. Electrons in this orbital would pull the nuclei apart, destabilizing the bond.
So bonding MO, good for bonding. Antibonding MO, well, bad for bonding.
Basically, yes. And both of these are called sigma MOs because the electron density is symmetrical around the line connecting the nuclei. Now for H2, you have 2 electrons total. Where do they go?
Into the lowest energy orbital available, right? So both go into the bonding Swann's MO.
Exactly. Giving an electron configuration.
Hmm.
Since the electrons are in a lower energy state than they were in the separate atoms, the H2 molecule is stable.
Okay, that makes sense. Does this model give us a way to quantify how strong the bond is, or if it even forms?
It does, and it's really neat. It's called bond order. You calculate it by taking the number of electrons in bonding MOs, subtracting the number of electrons in antibonding MOs, and dividing the whole thing by 2.
All right, so for H2, that's 2 bonding 0, antibonding 2 equals 1. A bond order of 1 makes sense for a single bond.
Perfect. Now try it for a hypothetical He2 molecule. Helium has 2 electrons, so He2 would have 4 electrons total.
Okay, 4 electrons. 2 would go into the bonding Swanns, and the next 2 would have to go into the antibonding Swanns.
Right, so the bond order is 2 bonding, 2 antibonding, 2 equals 0.
A bond order of 0, meaning no stable bond forms, which is exactly what we observe. He2 doesn't exist as a stable molecule.
See, the MO model correctly predicts its instability right away. It's very powerful.
That's really elegant. So how does this scale up to bigger diatomic molecules like in the second period N2O2, F2?
Good question. It gets a bit more complex, but the principles are the same. Now we're combining the 2s and 2p valence orbitals. The 2s orbitals combine to form SO2s and SOSODINOs, similar to the 1s. The 2p orbitals are interesting.
How so?
Well, one pair of 2p orbitals can overlap head-on along the internuclear axis to form SU-p bonding and SU-2p antibonding MOs, but the other 2 pairs of 2p orbitals are parallel to each other and perpendicular to the axis. They overlap sideways.
Ah, sideways overlap again. That sounds like pi bonds.
Exactly. They form pi molecular orbitals. You get 2 degenerate, same energy, 2p bonding MOs, and 2 degenerate 2p antibonding MOs. These have electron density above and below the internuclear axis.
Okay, so we build up an energy level diagram with all these sigma and pi molecular orbitals, and then fill them with the available valence electrons.
Precisely. And this is where MO theory really shines, particularly in explaining magnetism. Remember, substances with unpaired electrons are paramagnetic. They're attracted to a magnetic field. Substances with all paired electrons are diamagnetic, weakly repelled.
Okay.
Now, look at boron, B2. If you just fill the MO diagram based on the simplest energy ordering, you predict all electrons are paired. It should be diamagnetic, but experimentally,
Let me guess, it's not.
it's paramagnetic. It has 2 unpaired electrons. This was a puzzle. It turns out that for the lighter diatomics like B2, C2, and N2, there's significant mixing between the 2s and 2p orbitals. We call it PS mixing. This actually shifts the energy levels around.
How does it shift them?
It pushes the 2p energy level above the 2p energy levels for these specific molecules. So when you fill the MO diagram for B2 with its 6 valence electrons, the last 2 electrons go into the 2 separate 2p orbitals, unpaired, 1 in each.
Ah, so the refined model, accounting for PS mixing, correctly predicts the paramagnetism. That's a great example of how scientific models evolve to match experimental data.
It really is. And oxygen, O2, is another huge success story for MO theory.
How so? I remember seeing a demonstration with liquid oxygen.
Yes. The Lewis structure for O2 shows all electrons paired. It predicts diamagnetism. But if you pour liquid oxygen between the poles of a strong magnet, it sticks there. It's strongly paramagnetic.
So it must have unpaired electrons.
And the MO diagram for O2, even without needing the PS mixing correction that B2 needed, correctly shows that the last 2 electrons go into the 2 degenerate 2p antibonding orbitals unpaired. It perfectly explains why oxygen is magnetic.
That's fantastic. The localized model just couldn't explain that at all. And the MO model also links bond order to strength, right? Like N2.
Absolutely. N2 has 10 valence electrons. Filling the MO diagram, you end up with 8 bonding electrons and 2 antibonding electrons. Bond order 8, 2, 2 equals 3. A triple bond, correlating perfectly with its incredibly high bond energy and short bond length. This high stability is why forming N2 gas releases so much energy used in explosives.
It connects everything so nicely. What about molecules with different atoms like HF? Does MO theory explain polarity?
It does, beautifully. In heteronuclear diatomics, the atomic orbitals start at different energy levels because the atoms have different electronegativities. Fluorine is much more electronegative than hydrogen.
So its orbitals are lower in energy. It holds its electrons tighter.
Exactly. Fluorine's 2p orbitals are significantly lower in energy than hydrogen's 1s orbital. When they combine to form the bonding MO in HF, that bonding MO will be closer in energy to fluorine's 2p orbital and will have more fluorine character.
Meaning the electrons in that bonding orbital spend more time closer to the fluorine atom.
Precisely. This creates a partial negative charge on fluorine and a partial positive charge on hydrogen, elegantly explaining the polar nature of the HF bond directly from orbital interactions. And we can actually measure these orbital energies experimentally using a technique called photoelectron spectroscopy, PES.
Oh, interesting. So there's direct proof.
Yeah, the PS spectrum of a molecule shows peaks corresponding to the energies required to remove electrons from each molecular orbital. The spectrum for N2, for instance, matches the energy levels predicted by the MO diagram incredibly well. It's solid evidence. And think about something like capsaicin, the spicy molecule in chili peppers. Its structure, its polarity, how it interacts with receptors in your mouth, it all boils down to the shapes and energies of its orbitals, dictated by these bonding principles.
So we have these two models. The localized electron model with hybridization, great for visualizing bonds and shapes, kind of like the everyday workhorse. And the molecular orbital model, more powerful for explaining things like magnetism, bond energies, and delocalization, but maybe a bit more abstract.
Yeah, it's a good summary. Neither is wrong, they just offer different perspectives and have different strengths and weaknesses. But what if we could combine them?
How would that work? Where would you need to combine them?
Well, the biggest weakness of the localized model is resonance, right? Molecules where electrons are clearly shared over more than two atoms, like ozone, O3, or the nitrate ion, NO3, or benzene, the localized model forces us to draw multiple structures.
Right, the resonance structures.
The combined approach offers a more elegant solution. We use the localized electron model, with hybridization, to describe the basic sigma bond framework of the molecule, the strong, localized single bonds that hold the atoms together in their basic geometry.
Okay, so that sets up the skeleton.
Exactly. Then we use the concepts from molecular orbital theory to describe the pi bonding. If there are leftover unhybridized p orbitals positioned correctly, they can combine to form delocalized pi molecular orbitals that spread over multiple atoms in the molecule.
Let's take benzene, C6H6. That's the classic example of resonance and delocalization. How does the combined model explain it?
Perfect case. Benzene is a 6-carbon ring, each carbon also bonded to one hydrogen. We know all 6 carbon-carbon bonds are identical in length and strength.
Which Lewis structures can't show without resonance.
Right, so in the combined model, we first say each carbon atom is sp2 hybridized.
Okay, sp2 means trigonal planar geometry around each carbon 120-degree angles.
Exactly. Each carbon uses its 3 sp2 orbitals to form 3 sigma bonds, one to a hydrogen and one to each of the 2 neighboring carbons in the ring. This creates a flat hexagonal sigma bond framework.
The skeleton.
The skeleton. Now remember, sp2 hybridization leaves one p orbital unhybridized on each carbon atom.
Right, perpendicular to the ring plane.
Yes. And you have 6 of these p orbitals, one on each carbon, all standing parallel to each other, above and below the ring plane. These 6 p orbitals can overlap sideways all the way around the ring.
Not just between 2 carbons, but continuously.
Continuously, they combine to form delocalized pi molecular orbitals that extend over the entire ring. You get this cloud of pi electron density above and below the plane of the sigma framework.
Like a donut. The ring is the donut, the sigma bonds, and the pi cloud is like the frosting spread all over the top and bottom.
That's a perfect analogy. And this delocalized pi system is what makes all the CC bonds identical and gives benzene its special stability, its aromaticity. It neatly explains what resonance structures try to approximate.
And this idea works for other resonance-stabilized species too, like the nitrate ion, sigma framework plus delocalized pi system?
Absolutely. Any planar system where Lewis structures require resonance can usually be described this way. The sigma bonds define the shape, and the delocalized pi system explains the bond equivalency and added stability.
It really is amazing how these models let us visualize what's happening at such a tiny scale to explain macroscopic properties. It connects the invisible world of orbitals to the materials we use every day.
It really does. Think about someone like Dr. Nakul Bende, working in 3D printing materials. His job is literally to design and formulate molecules that will react in specific ways to form polymers with desired properties.
So he has to understand exactly how these bonds form, how strong they are, how localized or delocalized the electrons are.
Precisely. That understanding of sigma and pi bonding, hybridization, and potentially delocalized systems is crucial for developing new materials, whether it's for 3D printing, medicine, electronics.
Yeah.
It all comes back to controlling these fundamental chemical bonds. So looking back, it's really fascinating to see how our models for understanding chemical bonding have evolved, isn't it? We started with the localized electron picture, developed hybridization as a really clever way to make it fit observed geometries.
Yeah, a very practical tool.
And then moved to the molecular orbital theory, which gives a perhaps more fundamentally correct picture. especially for things like delocalization and magnetism, even if it's a bit more abstract.
And what's really striking is that it's not about one model being right and the other wrong. They're different tools, different lenses. Sometimes, like with benzene, the clearest picture comes from actually combining the strengths of both models.
Exactly. They complement each other.
Yeah.
And it really makes you think, as we keep refining these models and our understanding, how much better can we get at not just explaining the molecules we already know, but at actually predicting and designing completely new molecules and materials?
Materials with properties we haven't even imagined yet, potentially shaping future technologies from medicine to computing. It's a powerful thought.
It really is.
Well, thank you for joining us on this deep dive into the sometimes tricky but always fascinating world of covalent bonding and orbitals. We hope this helped clarify these concepts and maybe gave you some new insights.
Yeah, hope it was helpful. Until next time, keep asking questions and exploring those hidden structures that, well, make everything work.